Hello, my name is Andrew Zulu. Welcome to this presentation on two-dimensional equilibrium. We will cover the following: equilibrium types, free body diagrams, equilibrium conditions, 2 and 3 force members, and a brief discussion on constraints and statical determinacy, and then we'll look at some examples. Let's get started. So equilibrium is really at the core of statics. The study of equilibrium is the most fundamental pursuit in statics, as the subject itself is defined by it. Now let's look at equilibrium types and the free body diagrams. So we'll cover what is called the necessary and sufficient conditions for equilibrium, which are achieved when the resultant of all forces and moments is zero. So this will be done on a mechanical system, which is a body or a group of bodies which is isolated from all other bodies for the sake of the analysis of the system. So this isolation is achieved by what we call free body diagrams, which is really a diagrammatic representation of the system for the sake of studying it. So, but before we do free body diagrams, let's look at what types of equilibrium. So as you can see here in number A, we have a body here, which if you disturb it slightly, it will come back to its original position, so it's stable. This one, if it is disturbed just slightly, it's going to be very, very unstable, and this one is neither stable nor unstable, so it's in what is called neutral equilibrium. Let's look at free body diagrams. So free body diagram really is the most important single step for the solution of problems in mechanics. When you draw the correct free body diagram, it's likely that you're going to get the problem correct. So now, how do we draw this free body diagram? So first you decide which system to isolate, and then you isolate the system by drawing the external boundaries around the system, and then you identify all forces which act on the system. Very important, acting on the system. Then you choose the right coordinate system, and then you solve the problem. Let's look at the various types of forcing systems and how to draw the free body diagram. If it's a flexible cable, belt, chain, or rope, and the weight of the cable is negligible, like so, then you just draw a line in the line of action of the cable. If the weight of the cable is not negligible and is sagging like a catenary or anything like this, then you draw a line that is tangent to the catenary. If it's a smooth surface, you just draw a normal force without friction. And of course, if it is a rough surface, you draw the normal force together with the frictional force, where R here is the resultant between the normal force and the frictional force. If it's a roller support represented in various forms, then you just draw a normal force, okay, because the friction is negligible. If it's a freely sliding guide, like so, same thing, you just draw a normal support. If it's a pin connection, you have to represent both the unknown in the X and in the Y, okay, if it is free to turn. But if it is fixed, it's not free to turn, you also have to represent the moment. If it's a built-in support, like a cantilever or anything like this, then you have to draw the shear force, and then you draw the axial force, and then you have to draw the moment. Then if it is a weight, we know it's a uniformly distributed load on the object. What we do is we draw the concentrated load, which is acting at the center of mass, which is shown here. If it is a spring, whether it's a Hooke's law spring, F equals kx, or it's a hard spring or a soft spring, we just draw the force F acting on the object. Let's look at what are called the equilibrium conditions. So either of the three conditions that we see here will be sufficient for equilibrium. Summation of forces in the X and forces in the Y, and the moment at one point equal to zero. That's condition number one. Condition number two, summation of forces and summation of moments at 2 points equal to zero will be sufficient for equilibrium. Condition number three, you take moments at 3 different positions and set to zero, and that will be sufficient for equilibrium. The only catch on the third one is that the points A, B, C should not be in the same straight line. Indeed, if you get A, B, C in the same straight line, you're going to get the result that 0 is equal to 0, which is true, but not very useful, as you can imagine. Okay, now let's look at what is called the categories of equilibrium. So if we have collinear forces, for example, as illustrated here, F1, F2, and F3, they're in the same straight line. All we need to do is the sufficient condition for equilibrium here is the summation of forces in the direction of the line of action, which is x in this case. Summation of forces in the x is equal to 0. If the forces are concurrent, they meet at a point. For example, here F1, F2, F3, and F4, they meet at a point or here. Then there's no moment, because as you can imagine, all the forces are passing through the same point. Then we take the summation of forces in the x and in the y, and that is sufficient for equilibrium. Then if the forces are parallel, like in this case F1, F2, F3, then we take the summation of forces in the direction in which they are parallel, in this case x, summation of forces in the x, and then we take moments about an axis that's perpendicular to these forces, which in this case will be z, so summation of moments in the z equal to 0. If it's a general force system, for which is neither collinear nor concurrent nor parallel, we have all these forces all over the place here, then we have summation of forces in the x, summation of forces in the y, and summation of moments in the z, which is equivalent to this first condition here for us to get equilibrium. Let's look at what are called 2-force and 3-force members, very common type of members in statics. So 2-force members will be in equilibrium when the forces are equal and opposite, and they should be collinear. So for example, here we have the force F, the force F. This member here is in tension. These must be equal and opposite for us to get equilibrium. Similarly here, we have P and P. These members must be equal and opposite, and they're in compression in this case for us to get equilibrium. If you say 3-force member like this one, it's got 3 forces, F1, F2, F3. The 3 forces must meet at a point for us to get equilibrium. So the forces must be concurrent. Because if they are not concurrent, then they are actually creating a moment. And if the other representation of these 3 forces is that if you draw F1 and F2 and F3, they must form a closed polygon for us to get equilibrium. Let's look at what is called statical determinacy. So a constraint really is a restriction of movement, and what we call statical determinacy is whether we can solve this thing fully by the method of statics. So a statical determinate rigid body has more constraints. Statical indeterminate rigid body has more constraints that are required for equilibrium. For example, we have this beam here. If we have A and support C, we do not need B for us to get equilibrium in this case. So B is what is called a redundant constraint. So it can be removed and it will not have any effect on equilibrium. So the number of redundant supports gives what is called the degree of statical determinacy. This topic will be treated with equations and all in a later video. But for now, it's sufficient to say that the degree of statical determinacy is equal to the number of unknown external forces minus the number of available equations for equilibrium. So let's look at an example. Determine the reaction forces at the supports A and E of this system here. Okay, let's draw a free body diagram, the first step. So we get the reaction in the Y and in the X at A, and then we get the reaction at E. This is a roller, so just get one here. So obviously the first thing that we'll do is to take moments at this position A, okay, where we get more forces so that we can be able to get RE, and that's what we're going to do here. So moments at A will be defined in the following manner. So we have 350 sine 45, so the vertical component of this, okay, times this 4 meters perpendicular distance, plus 200 times 6, plus 300 times 1.5, okay, plus the 500 is a free vector, minus RE cos 45, which is the vertical component, times the sum of this, which I believe should be 12. When you do the arithmetic, you should be able to find that RE is 370 newtons. Then you take summation of forces in the Y. You're going to say RAY, which is what we're trying to find, okay, minus 350 sine 45, the vertical component, minus this 200, plus RE cos 45. Then the arithmetic there should show that RAY is 185.9, and then we take summation of forces in the X, it will be RAX plus 350 cos 45 plus this 300 minus RE sin 45 is equal to 0. The RAX should come out as minus 286. This simply means that it's actually 286 going in the opposite direction. Let's look at a second example. So we have member OCD and the pulley at D have a mass of 400 kilograms with a mass center at G. The mass center is right here. Calculate the magnitude of the force supported by the pin at O. Okay, the force here. Then it says also constraint at B provides horizontal support on this constraint here. Let's draw the free body diagram. Here it is. So we have the reactions at OX and OY, which we are trying to calculate. Then we have got the reaction at B here, and then we've got the weight, and then we're going to see what we have done here to move this force to a different location. So we transfer the 5 kilonewton force to the center of the pulley D. Okay, so when we transfer it here, we realize that we create a moment. That moment will be 5 times the diameter here is 0.5, so we get a moment of 2.5 kilonewton meters. Now let's take moments at O. Okay, so in kilonewtons to be 0.4 times 9.8 times this distance 1.2 minus this RB times 2 plus 1 plus 5 cos 30 degrees plus this times these two, 1.2 and 4.8. Okay, and then 5 sin 30 degrees, then you have to add 2, 1 and 2. Okay, and then you add the 2.5. Okay, that is equal to 0. When you solve for this, you should be able to find that RB is approximately 15.23 kilonewtons. Let's carry on. So that's our free body diagram here on this page. Then we take summation of forces in the X. Obviously it will be minus RB plus 5 sin 30 degrees minus OX is equal to 0. OX in this case you find it as minus 12.73 kilonewtons, which is 12.73 kilonewtons going in the positive X in this case. The same thing. The summation of forces in the Y gives us OY minus this one, 0.4 times 9.81 minus 5 cos 30 degrees. And then OY here, you should be able to find that it's 8.25. Then the Pythagoras of these two values gives you that the total reaction at O will be 15.17 kilonewtons. That's it for this segment. In this video, we have covered equilibrium types. We have done free body diagrams. We have done 2 and 3 force members. We have briefly looked at constraints and statical determinacy, and we have looked at some examples. This is all we have done in this course. Thank you for your kind